All right, today we're going to have a look at how the motor group with reduction works with the application from Cytec. We're running a servo controller 2 from Sidereal Technology, and we're going to have a little description of how this all works. What you see here is a brushed motor, which is here, and you see this cable, that is the encoder, is 500 ticks in quadrature, so every revolution it's 2000 ticks, and these are the power cable for the motor itself. They go in the controller like these, and the controller is connected with a USB cable to the laptop, and it's powered by a fairly simple power charger. Right, we are going to run it at 18 volt. These motors can run up to 24 easily. Just running it at 18 now. The way it works, or that is set up, we have this motor. I got rid of the original gearboxes, gear reduction that is coming with. These are motors mainly for robotics, amateur robotics. But these gearboxes are planetary gear setup, are usually coming with some backlash. I try to avoid as much as I can backlash. You can find between half a degree and 1 degree plus of backlash in these gearboxes. So in order to find that, I got rid of that, and I attach a belt, right, through a flexi joint. In this case, I have adopted bearings on both sides so that the load of the tension of the belt is not taking on the shaft bearing. So motor, bellow or flexi joint. Then we have, I think we're running a 20 to 60 or 50. So these are 2.5, roughly 2 to 3 gear reduction. I can remember exactly a few of these and several belt length. I have a system to tension the belt, and then this goes into this reducer. Now this is a little bit of a tricky reducer, special reducer. This is a 1 to 100 reducer, virtually backlash free. It's a so-called harmonic drive gearbox. So there's a total of 3 times 100. So this is in total 200 or 300 configurable gear reduction. The output of this goes through a bellow to the shaft that rolls on either the azimuth table or the bar that rolls on the altitude. I'll pop some CAD or pictures to show the position of these, but basically this is going on a friction drive. So again, we have a system that theoretically reduces the backlash as much as we can. All of this is set up on a 3D printed bracket or housing, whatever you call it. Right, so let's try it out. First thing first, we switch on the controller, and we move to the panel of the test and tune right here, and then we move this cursor. So the upper part is one axis, the lower part is the other axis. So right now we are set at 140,000 as a speed, which I think is 140,000 ticks per second. Right, and we can see the system that is working. It is rotating around. The motor is probably doing 2 or 3 revolutions per second. Now we can slow it down, and you see here that it's low down a lot. This is somehow a rotation of the main motor every 30 seconds or so. And if we apply some resistance here, the controller manages that pretty good. Then a little bit of a jerking, but only you can feel it only by hand. To adjust the PID parameter, to adjust proportional, integral, and derivative, I actually didn't change anything. So this is as it comes out from the original setup, and it works with this motor fairly well. It's important that the controller is able to move these motors very slowly, very precisely. Right, we can jump up by 1,000 times the speed. See the output shaft is rotating probably a turn every 4 seconds. We probably can increase these even more. With acceleration, we try to apply some resistance here. This will be the slewing probably. And it's pretty fine, pretty happy with that. And we'll turn that to almost tracking speed. Alright, pretty happy with this setup.